Then let's move on to the solar cell part. About 20 years ago, Professor Gratzel introduced a very innovative solar cell, which is inexpensive and um, can be very high efficient type of the solar cell, which could be potentially replace the silicon solar cell. So this is the general diagram for this. So this is called a virtual cell made of the TiO2 and the dye molecules, redox species, and counter electrode part. So what could happen here is light is eliminated, and then these dyes are used for light absorption. So after light is absorbed, the electron, excited electron, is injected into TiO2, and this electron moves toward the electrode and then coming back to the counter electrode side. And this electrode is due to the redox reaction, and then the redox species give back the electron to the dye molecules. So just keep illuminating the light. So electrons, meaning the current, is keep flowing inside this circuit. And this is very one of the quite nice idea to make this happen. And you could understand by drawing the energy diagram as we studied. So please stop the video and then draw the energy diagram in this case. Okay, then so what could happen here is, let's see, TiO2 here and solution side. No, not solution. Yeah, the solution side. So what happened here is that TiO2, when the TiO2 has a contact with solution, it's going to have most likely the Schottky contact, right? And as I mentioned in the photocatalytic applications, so when the light is illuminated and the electron on the holes are generated and then coming like that in a photocatalytic application. However, this one is inefficient because you need the UV higher energy for light, like UV light, and lambda must be like 400 nanometer. So UV light is necessary for this application. However, in the Gratzel cell, they use the dye molecules on the surface of TiO2, which is energy is somehow tuned like this. Energy level is tuned. And in many cases, at the initial study, ruthenium complex was used. For example, ruthenium bipyrazine 3-pipyrazine ruthenium. And this can absorb the visible light absorption. So you could excite this by the light and electron. Even by using the visible light, the electron is excited and it can inject it into the TiO2. So it's basically you don't have to use the UV light by this case. And as the back contact to the wire, as I mentioned, it's going to be like ohmic contact. And it is connected to the platinum side, but as you mentioned, the Fermi level must be matched for platinum. And there are some redox species. And mostly iodine redox species used. And this could accept the electrons. And this, when the energy level is adjusted, the electron can be given back to the ruthenium complex, and then it keep rotating. So it's a very smart way to, just by adding the dyes on the surface, electrons, charge carriers are moving around. That's what happens. So finally, and this is another very active topic, which is organic solar cells. And then I would just briefly mention what could happen for this. So this is another type of very smart way to make solar cells. And as you could see from the name, so it is purely made by, not purely, except electron. The solar cell part is made of the organic materials. And what happens here is two type of the conductive polymers have a contact and sandwiched by the electrode. Okay, and then from one side, they use the transparent, the electrode is used, and light is illuminated. And inside the donor or acceptor, you can excite the electron hole pair, and which is called exciton. So it's a kind of difficult for you probably, but it's a kind of excited state of the electron holes. But of course, electrons and holes has a positive and negative sign, and they have some interaction each other even under the excited condition, and they move together, and they come to the interface. And at the interface, the electron is going to electron side, and at the interface, the electron and holes are separated at the interface. And this could also give one of the highest the efficiency of solar cells. And in many applications, the fluorine are used to fluorine or related materials are used for electron donor. And P3HT, which is a geofilm-based polymer, this one also used for the hole conductor. And so these are the typical combinations, but there are many different types of the molecules have been developed recently. And to increase the efficiency of this, there was some innovation for actually just by mixing these two types of polymers in a nanoscale like this. So these kind of things are increasing the interfacial area that could enhance the efficiency of the charge carrier extraction. Then this type of the junction is called the heterojunction solar cells. Okay, let's finish this. So in this lecture, we studied several different the fundamental aspects of the photocatalyst, water splitting, and solar cells. Okay, with that, let's finish this lecture.